Hi everyone, we are back and we are now going to solve our first problem on our exam 2, question 1. So, red material behaves like a polymer, thermal expansion coefficient 4.8 times 10 to the minus 8. Red material symmetric to 2 rigid lubricated walls. Force in one direction is 280 kilonewtons. Final length in 3 directions is this. Temperature decreased from room temperature to 20. So, coordinate system, Young's modulus, 1 gigapascal. Our Poisson's ratio is equal to 0.4. Let's set up our stress and strain tensors. Our stress components, we're going to have a stress in the 1, 1. Oops, let me just stress in the 1, 1 here. There's going to be a stress in the 3, 3. And we know that there's going to be a strain in the 1, 1. There's going to be a strain in the 3, 3. We actually know the strain in the 3, 3 because we're given that final dimension, so we can calculate this. We know the stress in the one direction because we're given the force here. When we pull out here, and we decrease temperature, meaning it contracts, that there's definitely going to be a strain in the 2, 2 here, and it should basically pull in, and there will be no stress here. So let's go ahead and let's solve this problem. So I'm going to go ahead, pull up my Mathematica notebook. So here we define our Young's modulus. Here, del T is equal to 20 final temperature, room temperature to this, so 20 minus 25, 4.8 times 10 to the minus 8, that's going to be our ET. We've defined our initial dimensions everywhere, and I believe that those look to be all correct. The force in the one direction is 280 times 10 to the 3. We have our area. We are sigma 1, 110 times 10 to the minus 3. Sig 2, 2 is there. So let's make sure what are our unknowns in this problem. Our unknowns are going to be sig 2, 2, or actually not sig 2, 2, sig 3, 3, epsilon 1, 1, epsilon 2, 2, epsilon 1, and we can go ahead and shift enter here, here, and here. So we have sig 3, 3, epsilon 1, 1, epsilon 2, 2. Let's go ahead and shift enter that. And makes sense. Strain in the 1 is positive. 2 is negative because it should be kind of squishing in. And the stress in the 3, 3 is positive and quite large. Fantastic. So those are our stress strain tensors. What's the rotation to get to principal stress? That is going to be 0 because we're already in principal stress. Rotation to maximum shear, that's going to be 45 degrees. What are the respective values? Well, these are the values of my principal stress. My value of, actually we can define it. Let's go ahead and define it right now. My sig 1, 1 is this. My sig 3, 3 is equal to this. So which one is slightly larger? Actually, control here. So now I can say my sig 3, 3, my maximum shear stress will just be sig 3, 3 minus sig 1, 1 divided by 2. And there we go. We've got it. And you could prove that multiple different ways, but that will be my maximum shear stress value. Done. Are we in plane stress? Yep, we are in plane stress in the 1, 3 plane. Fantastic. Turns out the walls were not entirely, everything else is 0 because we're lubricated. Turns out the walls were not entirely frictionless. We have the engineering shear strain. Actually, this should be shear stress. That's a little bit of a typo there. Engineering shear stress was measured such that it was minus 64. Write out the new 3D stress and strain tensors. What is the rotation of principal stress now? We can't rotate this because now if we have a sigma 2, 3, we are no longer in principal stress, but we will have a strain in the 2, 3. So we can solve for that, and we definitely have to solve for that. So I'm going to solve my epsilon 2, 3, set that equal to 1 over my Young's modulus times 1 plus nu times sig 2, 3 is minus 64 times 10 to the 6. Multiply. I'm just going to put this here. And there you go. That's my strain in the 2, 3. Fantastic. So can't answer the rest of that. Now it turns out they were entirely frictionless, and energy shear strain was measured to be minus 13%. So now I have an epsilon 1, 3. I'm going to do the same thing here. So I need to say solve. Actually, just copy it in. So now it's minus 15%, so minus 0.15 equals this times nu times, what is it, sig 1, 3. So now I have this as my sig 1, 3. So I've got sig 1, 1, sig 1, 3. So now I am still in plane stress. I'm not in principal, so my sig OG is going to be equal to sig 1, 1, sig 3, 3, sig 1, 3. And I now need to go up, and I need to shift enter this part of the notebook, because now I need to find rotation to principal stress. Oh, that was so nice. I didn't even do the rotation to maximum shear stress. So now I need to do T.sig OG. And then I'm going to pull out the third equation. And I'm going to solve when does this equal to 0. In terms of theta. And there you go. And we can double check that. T.sig OG slash dot theta goes to and 0. These would be my maximum shear stress values, or maximum principal stress values. That's it. Not a bad first problem. And we'll see you on the next one. Thanks. Bye.